Cool, hello there. Today we're going to look at solving Olympiad geometry without human demonstrations. This is a paper that introduces the AlphaGeometry model. It's by Google DeepMind, and it, akin to other computer mathematics papers, it goes after Math Olympiad problems in the domain of geometry, specifically Euclidean geometry, and it does so, and that's what it says here, without any human demonstrations as training data. This paper is certainly a kind of a breakthrough in computer mathematics on one hand, but on the other hand is also super duper specialized in a way. Like the premises, like the circumstances have to be exactly right for this technique to work. And we're going to look into what they do right here. They say the combination is a neuro-symbolic system that can, so it's a combination of sort of trained language models and symbolic solvers that together do something like a proof search across these geometry problem. And specifically, the difficulty in these problems is the construction of auxiliary points or auxiliary things. And what that means is, I believe, demonstrated here in this example. So the top is a very simple problem that serves as an example. So they say, let ABC be any triangle with AB equals AC. So this is an equilateral triangle, like a triangle. So this here is equal to this here, right? Now we should prove that the angle at B here is equal to the angle at C. How can we do that? The ultimate proof is going to look like this. We construct the midpoint here, and we observe that AB equals AC. So that's a premise. We observe that BD, so this distance right here, is equal to this distance right here. And obviously AD is AD, and therefore we have two similar triangles, and therefore these angles have to be the same. You'll notice that the proof of why the angles are the same was included this construction of the midpoint right here, the midpoint D. So introducing new things in order to make the proof happen. This is done in a lot of mathematical proofs, like to introduce some helper variable, to introduce some kind of construction, whether that is in geometry or outside of geometry. Usually it's in the form of some definition or some kind of lemma or something like this, or yeah, as I said, an extra variable. In geometry, it's often the construction of extra points, extra circles, and so on. Like, oh, okay, take the bisector here and intersect it with this line, and we'll call that new point E, and then we'll, apply something to that point E. This is the difficult thing. Why is that difficult? Because if you have a math proof engine, it can only reason across the things that exist, right? As soon as it comes to, I need to construct something that doesn't exist first, and then I can apply my deduction rules to that. That's very tricky because the amount of things you could construct that aren't there already is infinite. And therefore, what should sort of a classic prover even do? It cannot even start searching, because even a single step, you have infinite possibilities to search for. So what the AlphaGeometry paper does is it says, how about we use a language model to suggest new things to construct, to suggest these auxiliary constructions, and then once we add them, then we use our prover in order to try to solve the proof. And if it can't solve the proof, we use the language model again to suggest the next thing to be constructed. We add that, we use the prover again, ask like, yeah, can you prove it now? No, okay. And they keep adding things until the prover can prove it. So this is the core loop here. You have a symbolic deduction. If it is solved, all good. If it is not solved, go here, ask the language model, what extra thing should I introduce into the construction? Give it again to the symbolic deduction engine, and repeat until solved. You'll already see this. We'll get into how you train the language model and so on to do the correct thing. You'll already see this requires an extremely specific set of circumstances. Namely, it requires that whenever, let's say, a problem is solvable with the current things you have available, then the solver here is able to, at least in reasonable time, give you that solution, right? It is also necessary that the language model can be trained to reasonably suggest next things to construct. That's also not a given by any means, right? It's been long held as sort of the creative act of mathematicians to introduce new things that are then helpful, and abstracting this into a language model, especially without human training data, as this paper does, requires a specific set of circumstances. You can see this applied to an actual problem here. So this over here is the problem statement. You can see it's quite a bit longer than the sample problem statement we've started with. Ultimately, you are required to prove that the circumcircles O1 and O2, which are in green here, and of the triangles FKM and KQH, so FKM maybe, yeah, and KQH, well, I don't even know where they are. Q, K, Q, H, these ones right here, so that the circumcircles of triangles FKM and KQH are tangent to each other, so that there's a point where they touch, I guess. All right, this requires AlphaGeometry 109 proof steps and includes quite a number of auxiliary constructions, which you can see right here. For example, this midpoint of BH, the midpoint of HC, and this other midpoint right here, among other things, I would guess. So as you can see, not an easy thing to do once you actually get to the hard problems here. All right, how I think the general structure, though, should be clear, right? So you start with the problem. You have already a solver in place, like a symbolic solver that can give you a solution if there exists one with the current set of premises and things you have available. If that does not yield a result, you add something. And adding something, that's done by a trained large language model. So now the question is, how do you train a large language model to suggest to add things to you? The first question is, how do you even encode such problems in a viable form? Now you just have to go with the flow here. Believe me that they have found the form to relatively efficiently and understandably encode this into a sort of language form where they can tokenize it and feed it into an LLM. The LLMs they're going to use right here are exclusively trained on this kind of domain-specific language. So they're not fine-tuning something that exists somewhere and rely on its pre-training or anything like this. As far as I understand, they fully, from scratch, train the model on the language on the DSL they construct here. What they do, they sample what they call random premises. And random premises are really just things like this right here. So they just construct a bunch of triangles and circumcircles and midpoints and angle bisectors and so on. And you can see in this extended table down here somewhere all the things they use to sample them. Again, they do not use this from human data. Where is it? This one. There's no human data in here. They just go about this and they just say, okay, I can sample an angle bisector. I can sample an angle mirror. I can sample the incenter. I can sample to make the tangent. I can make a line or a point on the line. I can make a segment of a circle, or I guess a segment at all, like just a line. So they can sample all these things, and you'll see, even though it's quite a list, it's not a giant list. So I think crucial condition number 2 is that the sort of base operations of the problem is relatively small. So what they're going to do is they're going to just sample combinations of these. Like they'll just sample like this. They start with this one and then maybe this one, and maybe some become impossible after a while because there is no line to put a point on. But once there is, these open up again. So they'll just kind of sample these, and they'll augment them by what they're called algebraic reasoning. So like dividing angles into half or multiplying them by 2 and things like this, like introducing constant factors and so on. But ultimately, it's a finite, relatively small set of things that all of these geometry problems are representable as combinations of. Right? At least a large part of these problems are representable as combinations of those things. They purposefully do not cover all of the geometry problems they encounter. They say only about 75% of their ultimate test set or of their of sort of the domain they consider is coverable by their DSL and by their constructs here, and they on purpose leave away the others. And I'm going to guess in order to keep things interpretable, but also in order to keep this list here that they need to sample from small. So why is it important that this is a small list? Because this being a small list makes it possible such that I can kind of cover the space that I'm looking at relatively okay-ish with just sampling from this. So if I just consider proofs that are 100 steps long, and I just randomly sample from, these things 100 times, and I do that 1 billion times, that's going to give me reasonable coverage of my domain. Not great, but reasonable, such that the LLM can learn something. If this here was, let's say, all of mathematics, or would have to cover all of mathematics, there would be kind of no way, I think, to do that. But because the fundamental elements of the domain are so limited, this is all of a sudden accessible. So that's what allows them to do this. So they just kind of go wild, uniformly sampling across these things, because again, they don't want to use human demonstration data. So they just uniformly sample random, what they call premises. So this here could be a construction of these premises. And I made a small mistake before. How many of these basic elements you sample to construct the premises is not directly the amount of proof steps involved to prove them. So I want to revise that statement, but there is a correlation. What do they do now? So now they have this construction right here. The second step they do is they figure out all of the things that they can say about this. So using their symbolic prover, they now prove like everything they can about this. So you can see right here, for example, there is a right angle here, and then there is, I don't know, I guess this is a triangle, and then this is a triangle, right? So one thing you can claim is that, triangle A over here and B are in some way similar, are they? I don't even know. But I hope you understand what I mean. Like from what we've constructed right here, we can go ahead and then use our symbolic reasoning engine to give us sort of the closure of all the statements we can now prove about this thing in total, right? So they call that symbolic deduction, to prove all the statements. And by doing that, they kind of they need to go, they built these trees. So, okay, we can prove that EADH, this polygon right here, EADH is cyclic, which I think means it has a circumcircle, which you can know by, I guess, looking that this here is a triangle, and if this is a triangle and you kind of intersect it in any way, then this must have a circumcircle. I'm not sure, but I guess that's what it is. So you can deduce this. Likewise, you can deduce that EBCD has a circumcircle. So if you consider again EBCD, this one, again, this can be completed to a triangle, and therefore it has a circumcircle. I think that's why it has a circumcircle. Then you can also deduce that, for example, this angle is equal to this angle, so EDH, the angle at D between E and H, is equal to the angle C between E, so to this angle right here. You can deduce from this being cyclic, you can deduce that these angles must be equal, because these are similar triangles. Maybe it's just the angles that are equal. You can deduce that some things are orthogonal. You get the point, right? So you can deduce things, and from the things you deduced, you can deduce other things, and you just do that until you've exhaustively made all the possible statements, all the possible non-trivial statements you can make about the things that you start with right here. Okay, that's step 2. That's symbolic deduction. All right, so now we have all those things. How are we going to do that? What are we going to do now? We're going to pick one of them. Okay, so we're going to pick of all the things we've proven. And you can see all the things we've proven out here represented by all these arrows, even the gray ones right here. Now we're going to pick one of them. This one here. That's the one. And we just say, okay, this one is now our target. This is to be proven. Okay. Once we've done that, we can simply walk back the path that the prover took to get here in order to obtain the proof, right? In order to prove this node right here, I need to know 3 things. I need to prove this here, I need to prove this here, and I need to prove this here. Well, the bottom one I can directly deduce from the premises that I have, but then the other 2, I can again trace back my steps and say, okay, I need to prove this and this right here. And these 2 I can then, prove from my original premises. All right, why does this help? I'm sorry, this is a bit of a long-winded thing, but at this point you can say, okay, great. Now you have kind of the target and you know the proof to get there. So this, you can ask, don't we have, isn't this exactly why we have the prover in the first place, to kind of find that path? Like, why does that help us? And now comes that 3rd step. You can say, okay, all the green ones are involved in proving this right here. Now let's look at what we actually have here. We have H and A and B and C. So we have 4 things. H, A, B, C. 4 things. H, A, B, and C. So these are the 4 elements, let's say, that we want to prove something about. Let's look at all the elements that appear anywhere in the proof. So these are A, H, we already had these, B and C we already had, but we also see other things appearing on the path to the thing we want to prove. For example, E and D. In fact, those are the 2 things that appear extra. So you can see out of all the things we have available here, only 4 of them appear in the thing we want to prove, but 6 appear on the way to achieve that proof. And we're interested in that difference. So E and D are on the way to the proof, but they're not part of the thing we want to prove. And since we've constructed this thing here out of kind of combining these premises, these construction premises in that list before, this means that we can now make this into a math problem that requires the solver to construct something. How do we do that? We simply take the problem and we only reduce the original construction down to the things that we want to prove something about, right? So in this case, only B, C, and A, the triangle, and H, right? And we ask, please prove that HA, this thing right here, is perpendicular to BC. And if we do that, in order for you to prove this, you will need to construct the points E and D along the way to your proof. I hope you can see a little bit how that works. So step one, we use this list of constructions, and we sample at random to construct something like this, right? That by definition means that anyone could construct these things, because you can just say, well, let's just construct the midpoint of this and consider it, right? And so on. Then we do a kind of a closure of all the things we could possibly say about what we've constructed. This is the symbolic deduction part. Then we pick one of these and we do what they call a traceback. The traceback is we'll look at all the nodes that are required to prove the statement that we picked. Now, what we can do is we can say which elements of the original problem are part of the final statement, and which elements of the original problem are not part of the final statement, but are somewhere part of the proof. And the ones that are not part of the final statement, but somewhere in the proof they appear, that directly leads to the formulation of a problem, which is, you can see this is not the same as the original thing. This is derived from it. So I can now leave away everything except the things I want to say something about. And by having the people prove that statement, necessarily they will need to construct these auxiliary constructions along the way, because those are on the way to the proof. They can be constructed because that's how we originally did it, and they are not already there because they're not in the final statement. So that's how they come up with a data set that requires these auxiliary things to be constructed in order to prove something. That's it. That's how they make the data set. I think that's pretty smart. You can see totally that it requires this very specific set of circumstances, like, okay, the problem domain is kind of infinite, but also the list of basic premises that you can combine to achieve these premises is sort of very small, and also it can be verified easily and so on. But still, I think it's pretty smart how they did that. So yeah, you can see right here, points E and D took part in the proof, despite being irrelevant to the construction of HA and BC. Therefore, they are learned by the language model as auxiliary constructions. So now we're just going to take the language model and just going to feed those derived proofs into them. And we're going to weigh the ones with auxiliary constructions specifically. Notably, they pre-train on all the proofs and then they fine-tune on the ones with auxiliary constructions, so that the language model is kind of heavily based towards making these auxiliary constructions. And yeah, that is how they come up with a language model that can then suggest to construct new things. All right. Yeah, this all here is just saying that. They say, okay, the sort of the key missing piece is generating new proof terms. Sort of, if you want to do computer math, they're very good at this symbolic deduction, but they're not good at suggesting new things to feed into the symbolic deduction. And yeah, the proofs perform auxiliary constructions that symbolic deduction engines are not designed to do. And if you make them consider them, then that introduces infinite branching points to the search tree. So even in the first step, you have infinitely many things to consider. Not just many, but like infinitely many, because constructing new things is a wide open domain, like infinitely open. The language model is seeded with the problem statement string and generates one extra sentence at each turn, conditioning on the problem statement and past constructions, describing one new auxiliary construction, such as construct point x so that ABCX is a parallelogram. Each time the language model generates one such construction, the symbolic engine is provided with the new inputs to work with, and therefore its deduction closure expands, potentially reaching the conclusion. They look a little bit into the data they have generated. The proofs, they are skewed towards shorter end of the proofs, but here you can see sort of the average proof length and very long proofs, but still you can see there are enough proofs in the data set that surpass that, although this is a log scale. But suffice to say, they do manage to cover the domain okay-ish, and okay-ish to the degree that the proofs they generate are at least sometimes long enough or even longer than the proofs that are necessary to solve these Math Olympiad problems. Yeah, I don't want to go too much into this. The notes are available to Patreons as always. I want to go a little bit into the results. They consider 30 Math Olympiad problems as a benchmark, and previous methods solved kind of not as many, while as their system solves 25 of them. Of the ones they didn't solve, I didn't, maybe I've overread it because Nature papers are a complete, like, I really don't know how someone can read those papers and sort of orient themselves in it, because it's like 5 times over the same thing, but then it's always a bit different, and oh, this is the methods thing. And in any case, I have not seen them deeply look at the ones where it failed and explicitly say, you know, here is why it failed. Were they not representable? But I think the ones that are not representable in the language, they've already excluded from the 30. So I don't exactly know the 5 they couldn't solve, kind of why. And that would be interesting, but maybe that's in the paper and I haven't seen it. They also say they could do some ablation here. They say, oh, the funny part is, okay, GPT-4, 0. They say if we only use 20% of the training data, AlphaGeometry still achieves 21 problems solved. Similarly, if we only use less than 2% of the search budget, so a smaller beam search, during test time, AlphaGeometry can still solve 21 of the 25 problems. So the way to read that is they got to the 2021-ish mark of solved problems pretty quickly, but then they pumped a lot more compute data into it, and that gave them 4 more problems respectively without fine-tuning. You can see that they solved 23, so they're like, okay, let's fine-tune on the ones with only the auxiliary constructions, and that gives them 2 more. What that suggests to me, so they frame it here as, oh, if we only use 2%, we still achieve state of the art. I read that as we pumped a lot more compute and so on and data into it, and we only got very marginal returns for it. And that kind of suggests there might be a sort of a ceiling to this where you'd have to, in order to maybe solve the 5 remaining ones, you'd probably have to invest humongously more resources. I don't know. That's just how it reads to me. If they don't frame it as sort of, oh, we can still do really well with a smaller budget, it's okay, we couldn't do really well even with a bigger budget. So here you can see the procedure. We pre-trained the language model on all 100 million synthetically generated proofs, including the ones that are pure symbolic deduction. We then fine-tune the language model on the subset of proofs that requires auxiliary constructions, which was about 9 million proofs. So about 10% of the total data had this auxiliary construction. Briefly going over the rest of the paper right here. I hope you kind of get what they did now and how they did it, but there are some interesting other bits in this paper. For example, the proof length for hard problems, at least, seems to correlate with the average score of human contestants. You can see as the problems get longer, sort of in terms of proof length, humans also score less on them, which makes sense. Like it kind of makes sense if someone says this, but it wasn't necessarily obvious that this is the case. But it could also have been that they're just more difficult. But then again, if you consider there are super few, like the amount of actual different things you can do in this domain is very limited, it does make sense that kind of the main way you can introduce difficulty into this domain is just by making the required proof steps longer. And you can also see that all of these very difficult problems did require some sort of construction. In fact, the ones that are only deduction tend to be the easier ones, at least, here. Yeah, so yeah, I think this is a domain where just hardness of problems correlates probably more than in most other domains with just how many steps are required to achieve the goal. And your goal is just that humans aren't that good at kind of doing that search problem over very long steps, looking very far into the future in a search tree. Good, they say, yeah, something about how they represented. They purposefully don't use a formal language that can represent kind of general math problems such as lean. They say that requires a large amount of groundwork to describe these problems. So they say we instead adopted a more specialized language using in these other papers and these other works or other systems. And owing to that, 75% of all the problems can be adapted into this representation. Every proof step is logically and numerically verified and can also be evaluated by a human reader as if it is written by an IMO contestant, thanks to the highly natural grammar of the language. So that's one thing that's certainly pretty helpful in evaluating these things. As you can see in the proofs that I've shown you, at least, it did look and sound interpretable, right? The proof here on the top right, we could read it, right? So the top thing here is a construction, right? It's very, very readable from a human standpoint now, and obviously also tokenizable once you get to it. And then these things right here, the premises and the inferences and what that means, all of that is quite readable and interpretable as a human. And that also allowed them to do human rating on their solutions. But yeah, so that's certainly an advantage as opposed to doing it in something like lean, where probably already this proof would be quite large and quite not understandable by human standards. But the other reason is certainly that this being so limited, limits a lot their premise construction sort of breadth. And second of all, is much more conducive to the language model because the vocabulary is limited, and with the same amount of data, you can cover a lot more sort of valid sequences if the vocabulary is shorter. All right, I don't want to bore you too long. They are still like a tiny bit worse than the gold medalists on this, but they are probably better than most humans, especially most untrained humans. So take that as you will. This is, as I said in summary, this is a paper that does a very good job at a very, very specific niche application. And I guess the biggest question here is this technique that they used, how reliant is it on the specifics of this domain, and how applicable is it to a more sort of general, how applicable is it to more general problem settings? Or if we ask another way, what other problem settings exhibit the same core fundamental elements of this technique such that it is applicable, right? I'll leave that up to someone else to decide. I wish you a very pleasant evening. Thanks for listening, and bye-bye.